Hello everyone, my name is Vinicius Mattoso and I present the work developed by me, Dr. Demir Maza, Professor Belado, and Márcio Carvalho. This work is called the Reservoir Characterization Comparing Different Ensemble Methods. This work is a part of my master thesis. This work is inside of the reservoir management area, and more specific inside of the reservoir characterization. In a summary way, a reservoir characterization means to estimate the different properties from the reservoir, such as the different permeability values and regions. To make possible the characterization, some data is necessary. To obtain this data, the well tests are commonly made. This test consists in the controlling process of opening the production valve during the period called the drawdown followed by a static period called the build-up. During the whole test, the pressure and temperature data are registered. Despite we have good resolutions for pressure and temperature data, commonly only pressure data are used to make this reservoir characterization. The problem consists of estimating the permeability of the reservoir based on data. For this, we create a simulated data with non-permeability values, and then we use an optimization method to make their history match and estimate the values for its permeability. So, in order to estimate a range of value as response, we use an ensemble of simulated model and use an ensemble-based method to make the history match and achieve a range of values as a response for each parameter. The main goal of this work is to compare the reservoir characterization using the genetic algorithm, the ensembles mutual, and the ensembles mutual with multiple data simulation method. To achieve this objective, we implement the ensembles mutual and the ensembles mutual with multiple data simulation method, and then we evaluate the computational cost and the parameter estimation for each method. An isothermal well reservoir simulator was used to build a set of simulated data. The LMMP group from PUC-Rio developed this numerical simulator using the finite difference method. It consists of a well-born coupled with a 1D cylindrical reservoir for a single-phase fluid flow. The observed data was captured from the sand phase, that is the connection region between the well-born and the reservoir. And to simulate the measurement data was add a normal distribution into the simulated data. In this work was used the ensembles mutual that make a single global update and the ensembles mutual with multiple data simulation that make many global updates. The update formula are similar less than alpha e, that is the inflection factor that obeys this formation rule. The CMD and CDD from both methods are generated in this way. The CD is the covariance matrix of observed data measurement error, and the Duke and the OBS is the observed data, and the D is the calculated or simulated data. The CD matrix used comprised of two diagonal blocks associated with each independent observed data. The first block corresponds to the pressure data, followed by the temperature data. The CD matrix used was created based on a SUI PhD thesis that used the Joule-Thomson coefficient to correlate the pressure and the temperature data into the Levenberg-Marquardt method. The CD matrix also has an addition of a weight of 10 power less 4, and to avoid scale problems, the pressure and the temperature data was normalized. The genetic algorithm is also an optimization method, and the population here is the ensemble of the vector of parameter. Each vector is a chromosome and each parameter is a gene. The operator of this method is the mutation that randomly change the value of one gene, and the crossover that make the combination of two chromosomes into new chromosomes. The fitness function used was the quadratic error between the observed data and the calculated data divided by the calculated data. This fitness function was used to avoid scale problems, and the optimization toolbox from MathWorks was used because it has this genetic algorithm implemented, and the crossover fraction was set 80% with the good results. The reservoir configuration analyzed was a homogeneous and single porosity cylindrical 1D reservoir. The observed data was captured considering 2 days of flow at a constant rate of 100 meters cubes per day, and the fluid properties and rock properties were extracted from Galvon works. Instead of sorting the permeability value, we use the log transformation to reduce the amplitude of the permeability values and give the Gaussian format that is required for the ensembles motor and the ensembles motor with multiple data simulations. So we use a normal distribution with mean 5 and a standard deviation of 1 to generate the log permeability for the ensembles motor and the ensembles motor with multiple data simulation. And for the genetic algorithm, we set a limit of 2.0 to 7.5. And for the porosity, was used a normal distribution with mean 0.2 and standard deviation of 0.05 for the ensembles motor and the ensembles motor with multiple data simulation, and for the genetic algorithm we set the limit of 0.03 to 0.3. So the configuration analyzed were the ensembles motor and the ensembles motor with multiple data simulations, considering coupled data, and for the genetic algorithm were set in pairs, one considering the coupled data and the other considering only pressure data, using 4 generations, 16 generations, and 20 generations. Let's pass to the results. And considering 4 simulations from the SMDA and 4 generations from the genetic algorithm, the SMDA provided an accurate result, and the ensembles motor with just a single update provided a better estimation than the genetic algorithm considering 4 generations. Increasing to 16 generations, the genetic algorithm, with both observed data, provides a better estimation than using only a single assimilation from the ensembles motor. And increasing to 20 generations, the genetic algorithm provides a simulation similar to the ensembles motor with multiple data simulation. And the use of combined data in black provided a better estimation of the porosity than using the single pressure data in red. So, as conclusion of this work, we have successfully implemented the ensembles motor with multiple data simulation and the ensembles motor method. Coupled pressure and temperature data can be used to estimate the reservoir parameters. The ensembles motor provides a better estimation than the genetic algorithm with 4 generations. And to estimate similar values, the GA needs to pass the ensemble 16 times more the ensembles motor with multiple data simulations. And as future works, we want to provide randomly initial guess to genetic algorithm and run many times with the same number of generations to evaluate the impact of the observed data. And we want to increase the number of parameters associated with the reservoir characterization. Finally, we'd like to say thank you for the attention and like to say thank you for those institutions for the financial supports.